Hello, welcome to the C++ instruction video called Tools. My name is Nico Punt and I will show you today the tool objects available in the C++ PKPD library. Okay, I will start with a very simple one compartment model. And let's do a simulation and we get this well-known profile. Okay, now I will add a tool, and the default tool is the integrator. So I will connect it to this compartment. I will double click here, and here if I look at variables I can select which integration value I want to see. I can observe the AUC or the average. Now let's go for the AUC. So I click here AUC and I simulate it now. So here you see the AUC value, and here's the original concentration. What I can do is I move the AUC to its own axis on the right axis, simulate it again. Okay, so here you see the AUC. I can also select the average concentration. So if I unselect this, I will select average concentration and simulate it again. So you now here see the average concentration. And what you can see is that the average concentration is reset with each dose. And that is controlled right here by the sync object. So the sync object synchronizes this integrated tool. And what we can do is we can actually simply remove this. And if I then simulate again, you see that you get kind of a moving average value. And the same is true for AUC. So if I would switch back to AUC again, it will simply keep on adding. So, but we typically switch on the syncing and we sync it to the event object. In this case it's the injection, so we sync it to dosing events so that we get this curve for the AUC and this curve for the average concentration. Another tool is the level monitor. So if I add here, I change this to level. And well, at this moment you don't see anything. If I do a simulation, okay, I want to look at the level. So here I have levels around, let's say, starting at 60, 80, and at steady state it's about 180. So let's say we want to monitor how long the levels are above, let's say, 140 milligram per liters. So what I do is here I enter a level value in the variable section. So I say 120. And I want to observe this level. So if I simulate this, so the only thing you get is this reference line for 120 and our original curve. So now I want to calculate the time above this level. And we have two variants of that. We have a relative time, so it's relative to the interval time, and we have an absolute time. So if I click now absolute time, and I would move it to the other axis, and simulate this, so you see here it says well, it will end up at around 4.2 hours above this level. And if you look closely, you can see at steady state that it's about correct. We can also say, okay, I want to see the relative time, so I remove this again, I select relative time on the alternate axis. So you can see then it comes up at steady state to about 50% above this level. I can also share the axis, and then we get this type of. So here you can see about 50% of the interval time, it's above the set level of 120. So an important application of the level tool is, for instance, if you have an MIC value for an antibiotic drug and you want to monitor the time above MIC. Okay, a more passive object here is what we call the reference tool. And the reference tool doesn't do any calculations. It's only used for showing some reference values. So if I say, for instance, let me look at the levels again. Okay, it's one about 180 and it is about 80. So if I say I want to have some reference line here, so 180 and for instance 80, and I want to show these reference lines, you have them right here. And of course I can change the colors of these lines. So I want to say, okay, I want to have the blue lines here, and here also a blue line. And if I simulate this, you have these reference values. And I could add, for instance, a toxic line. If it's, let's say 250 would be a toxic line. I want to show this, and I of course make it a red color. And if I simulate this, you get this. So this is in fact only used for presenting reference lines in your graphs. It doesn't do any calculations. Another object that's very useful is the addition object, where you can add two variables. So let's say that I add another compartment here, connection, and I connect it here as well. So what I want to do is I want to add the concentration in the central compartment to the concentration in the peripheral compartment. Of course, not that useful, but let's start this way. Okay, and if I simulate this, well, we only see now the concentration in the central compartment and the concentration in the peripheral compartment. We will now configure this addition tool. So we want to observe the sum. Simply click here, sum, and you see here the total. Okay, adding concentrations is not that useful. What is useful is, for instance, adding amounts in different compartments, so that you can use it as a kind of checksum for your mass balance. So what I can do is I configure again my addition tool, and I go to externals. And here you can see that the source for this object is concentration. So I can change this, for instance, to amount. And if I now do a simulation again, you see that here the red line is now the sum, but it's not the sum of the concentrations, it's the sum of the amounts in the compartments, as you can see by the unit here in milligrams. Okay, let's clean this again. And I will now show you the last object, tool object, and it's called the T polyexponential. And T polyexponential is a model on its own. So it's in fact a five compartment multi-exponential equation, and you can use it completely on its own. If you, for instance, here enter a dose, for instance the 100 milligrams every 8 hours, 10 dosages, and simply click simulate, and there it is. But the main difference, of course, with the other models we have seen so far is that these other models are based on differential equations, and of course are more flexible, have more possibilities. But still, this works very nicely. And if I look through the variables, you can see that I can observe the concentrations in different compartments. If I look at the parameters, you have the parameters of, for instance, the distribution parameters to the different compartments. Look at the constants, you have, for instance, here the fraction unbound. And here I have some options I can set. For instance, here I can change the route of administration. So if I select here extravascular and do a simulation again, we have then an extravascular profile. Now let's go back to the options. One important option you see here is auto init. And if you enable auto init, you set it to yes, then this tool, this polyexponential tool, is very smart when it initializes itself. It can investigate a standard AdSim++ model on the desktop and pick up the parameters. And in this way, we can use this tool to validate the correctness of the AdSim++ model. And I prepared an example of this. So here I have a simple one compartment model, but I did quite a complex administrations to it. So I have, for instance, here an injection. If I look at the schedule, so here 100 milligrams every 8 hours and then 30 dosages. I have an infusion, also 100 milligrams, starting after 40 hours in the simulation. And each infusion takes 6 hours at an interval time of 8 hours again and 20 dosages. And here the absorption, again 100 milligrams starting at 80 hours and again 3 times a day for 10 dosages. So these regimes overlap each other, so it's quite a complex model. Now, and what this tool will do, you don't have to connect it, you just put it on the desktop. Here, as I said, under options, auto init is set to yes, and that it will pick up the parameters, for instance, for absorption rate or the volume of distribution or the elimination rate from the differential AdSim++ model. And then you can simulate them in parallel, one using the differential equations, one using the Pauli exponential equations. And let's do that right now. Oh, one more thing I've got. I added an additional dose here to the Pauli and exponential equations. So at the very end, after 240 hours, at the very end of the simulation, I added an additional dose to the Pauli exponential equation in order to expose it, because you will see that the curves will overlap. So let's do the simulation. So you can see it here. It looks as if you have only one curve. But as I said, at the very end, I expose the Pauli exponential curve. So what I prove here is that those two simulations using completely different methods yield identical results, which I think proves that both methods are correct. It would be a very big coincidence if both methods were wrong and still yielded the same result. So I think this is proof that both methods are truly correct. And we can look at the output in more detail. So here's the Pauli exponential equations, and here is the differential equation results, and you can look at the values, and you can even do calculation on that. So for instance, I want to know what's the difference here. I would say, okay, this is D15 minus E15, and I can see how big the difference is, and it's very small, as you can see. So this concludes the video about tools.